everyone, this is Mrs. J. Today we're going to be solving linear systems, but first go ahead and pause the video and try this quick warm-up. Okay, so remember when we're solving absolute value inequalities, we isolate our absolute value symbol and then we determine if it's an and or. So this one is a less than, so it's an and. So we set up our two separate inequalities, and remember our answer has to be overlap of the two because it has to work for this and this. Now if you're looking for numbers that are less than or equal to -8 and greater than 0, you'll see that there is no overlap. There are no numbers that are both of these things. So in this case, our answer is actually no solution. And if you look at it, an absolute value, remember, make sure value is positive. So there's no way that this absolute value can be less than this negative number. So for part B, again, we isolate. This is a greater, so this is an or. So it has to work for this or that, meaning there does not need to be any overlap. Now when you solve the two separate ones, you get x is greater than 4 or x is less than 10. So if you visualize that on a little number line, you realize, hey, that's every single number. So in this case, our answer is actually all real numbers. All right, so we're going to start today's lesson by solving a two-variable linear system. So we essentially are going to have two linear equations, and our goal is to solve them, which is essentially finding the point of intersection of the two lines. So there's three things that could happen if you're looking for a point of intersection of two lines. It's very possible for two lines to cross exactly one time. So your solution would be this coordinate, this x and y value. But it's also very possible for two lines to never cross. So if two lines are parallel, meaning they have the same slope, they will never cross. So you actually have no solution to this system. And then it's also possible, you can't really see it in the graph, but imagine you actually have two equations that make the same line. Is literally the same line on top of itself. So when you have a case like that, you actually have an infinite number of solutions. So those are the three cases that we'll see with these types of systems. So we're going to solve these systems in two different ways using the substitution method, where we essentially isolate one of our variables and substitute it into the other equation. And then from there, we just keep back substituting until we can find the other variable. The second method we'll use is called the elimination method, or it's sometimes called the addition method. So we're going to line up our variables and constants vertically, and then we sometimes will need to multiply one or maybe both equations to create, here's the important phrase, opposite coefficients for one variable. So for example, we'd like it to say positive 2x, negative 2x, or negative 7y, positive 7y. Because if we do that and we add vertically, it eliminates one of the variables, and then we just are able to finish solving, and then we back substitute to find the missing variable. So we'll review both of these methods today. All right, let's give this first one a try together. So here we're going to solve this one using the substitution method. A good thing to look out for when you're deciding what method to use is if you notice that one of your variables is already solved for, like it is here. This one already says y equals. The substitution method is a great one to pick. So with this, since y is equal to 2x minus 4, wherever I see a y in my other equation, I can simply replace it with a 2x minus 4. And you guys will see throughout the year, whenever I substitute anything, I always do it with parentheses, even if the parentheses don't end up affecting the problem. I think it's just a really good habit to get into. So now if you look, I only have the variable x in my equation. So now this is just a normal linear equation, which I know how to solve. So I'll start by combining like terms, and then I'll add 4 to both sides and divide both sides by 5. So I have x equals 1. But I'm not done yet. I need to find y. So I'm going to take this x value, and I can actually substitute it into either equation. So let's sub x equals 1 into y equals 2x minus 4. Again, you could substitute it into either equation. So we have y equals 2 times 1 minus 4, y equals 2 minus 4, y equals negative 2. So now we have solved for both x and y. And then the last thing we're going to do is make sure we write our answer as an ordered pair, so it looks just like a coordinate. So this is how I would like you guys to write your answers when you're solving a system of equations. I just want to remind you, you can also check your solution by plugging both x and y into each equation and making sure the left side equals the right side. All right, now we're going to try solving a system using the elimination method. So here, again, we want to create opposite coefficients for either x or y. So you can see that right now, neither of them are opposite, so we're actually going to need to multiply both of our equations. So let's say we wanted to create opposite coefficients for my x terms. If you have negative 2 and 3, we know that the least common multiple of those two numbers would be 6. So I want this to be negative 6, and I would like this to be positive 6. So if I want this to be negative 6, I need to multiply it by 3. But you can't just multiply one term in your equation. You have to multiply both sides of your entire equation. And then here, I would like this to become a 6, so I need to multiply it by 2. But again, I need to multiply both sides of my entire equation. And then I'm going to rewrite both equations down below. So we have negative 6x, don't forget to distribute here, minus 18y equals 72. And then here, 2 times 3x is positive 6x, 2 times negative 5y is negative 10y, and then equals 40. So now you can see that we've created opposite coefficients for my x values. So if I add vertically, I get negative 6x plus 6x, and they cancel out, which is why we call it the elimination method. So remember, we're always adding here. If you have opposite coefficients, we're just going to add. So here we have negative 18 plus negative 10, so just be careful with that. It's negative 28y, and then we're going to add up our constants as well. And now we only have a single variable left, which means we are able to solve. So I'll divide both sides by negative 28, and I get y equals negative 4. Now to finish solving for x, I can substitute y equals negative 4 into either equation. It doesn't matter. So let's substitute it into our second equation. So 3x minus 5 times negative 4 equals 20. 3x plus 20 equals 20. So 3x equals 0, and that means that x equals 0. So now I can write that as an ordered pair, 0, negative 4. Now, just for practice, let's say instead of wanting to eliminate our x's, we decided that we wanted to eliminate the y terms because it's the same amount of work. So if I have negative 6 and negative 5 as my y coefficients, I know the least common multiple there would be 30. So I want to turn the top one into positive or negative 30. It doesn't matter. So I'll multiply it by positive 5. So this term would be negative 30. So I'd like this term to be positive 30, which means I should multiply it by negative 6. So if I do that, we get negative 10x minus 30y equals 120. And then we get negative 18x plus 30y equals negative 120. And then if we add vertically, again, we see that our y terms will eliminate. And we get negative 28x equals 0. So x equals 0, which is what we got using the other method, and then, or using our other strategy. And then again, we could substitute that into either equation. Maybe this time I'll substitute it into the first equation. So we have negative 6y equals 24. So y equals negative 4. So we get the same answer whether we decide to eliminate the x's or eliminate the y's. So for there, it's really what looks easier to you. And sometimes you don't have to multiply both equations. Sometimes you only need to multiply one equation, or if it's a really nice problem, sometimes you don't have to multiply at all. They already have opposite coefficients. All right, let's try another one together. So here we could either choose to eliminate the x's or y's. Again, it's about the same amount of work. So if we want to eliminate, let's say, the x's, I have negative 6x and 12x. So I know that 12 is actually the least common multiple. So all I would need to do is actually multiply my top equation by 2. So I'm still going to rewrite both equations. Don't forget to distribute the 2. So it's 20y equals 2. Then I'm going to line up the other equation right underneath. And I'm going to add vertically. Now here you'll see something interesting is going to happen. My x's cancel out, but my y's also cancel out. So that means the left side of my equation is 0. But let's see what's happening on the other side of my equation. 2 plus negative 2 is also equal to 0. So if both of your variables disappear, but you're left with an expression or an equation that is true, 0 is equal to 0. What that means is that we actually have infinite solutions. So really, we have two equations that make the same exact graph. Now, if you take each of your original equations, let's look at the first one, and let's rewrite it in slope-intercept form. So we have 10y, I'm going to add 6x to both sides, and then I'm going to divide by 10. We have y equals 6 over 10x plus 1 over 10. I can simplify that a little bit, 3 over 5x plus 1 over 10. Now let's rewrite our second equation in slope-intercept form. So negative 20y equals negative 12x minus 2. Divide both sides by negative 20. So we have y equals, and then if we simplify this equation, we get 3 over 5x plus 1 over 10. So you can see when we rewrite both of our equations in slope-intercept form, we actually get the same equation, which is why both of these equations make the same graph. So again, when you have a scenario like that, we say that there are infinite solutions. Algebraically, again, what you will see is that both variables will disappear, and you'll be left with an equation that is true, like 0 equals 0. Now let's try one more together. Here, again, we can eliminate our x's or our y's either way. Maybe this time, let's try eliminating our y's. Here we have 10y and 5y, so we know the least common multiple would be 10. So if I multiply my bottom equation by negative 2, that will give me negative 10y, so then they can cancel out. So I'm going to rewrite both equations below. 8x minus 10y equals negative 26. So if I add vertically, my x's cancel out and my y's cancel out, so I'm left with 0. But here, 21 plus negative 26 is negative 5. So here my variables disappear, but I'm left with an equation that is simply not true. 0 is definitely not equal to negative 5. So when we have a case like this, that means that there's actually no solution to this system. So why is this happening? Now again, if we take each equation and we rewrite it in slope-intercept form, so 8x plus 21, I'm going to divide both sides by 10. So we have y equals 4/5 x plus 21 over 10. And then let's rewrite our second equation. 5y equals 4x plus 13. Y equals 4 over 5x plus 13 fifths. So if you compare these two equations, you have two equations that have the same slope. So notice that they have the same slope, but different y-intercepts. So they are not the same equation. It's not the same line sitting on top of itself. But since they have the same slope, that means that they are parallel. So anytime you have two lines with the same slope, you have parallel lines. So we know that parallel lines, again, will never cross, which is why we have no solution. There is physically no point of intersection between these two lines. So now that we've done a little review on how to solve a system of 2 variables, now we're going to be solving a system of 3 variables. They're still going to be linear systems, but now we're going to see x, y, and z. So when we're solving a system of 3 variables, we are looking for the point or points of intersection, just like we were before. But this can kind of occur in different ways. So when you have a 3 variable system, it's in 3 dimensions. So it's very possible to have the three planes that are created cross at one single point like you have here. So it's still very possible to get one solution, but it's also possible for the 3 planes to cross infinitely. So it would just be this line that continues forever. So it's also possible to have infinite solutions with these types of equations. And just like before, it's very possible to have no solution. Remember, we're looking for where all 3 planes cross. So even if 2 of them are crossing at any individual point, that's not a solution. We're looking for where all 3 are touching at the same time. So again, here you may get one solution, infinite solutions, or no solution again. So we are going to be using an elimination method to help us with this. Very similar process, except here we have to eliminate one variable in 2 different ways to start. Once we have done that, we have a system of 2 variables which we know how to solve. So from there, you can use the method of your choice and you can just keep back substituting. You'll see for these, I have a very specific way that I'd like you to show and organize your work. So make sure you're doing it exactly how I'm doing it in the notes. All right, let's try this first one together. So here I have my 3 equations, and you can see they have 3 variables, x, y, and z. So these can get a little bit messy, and it's really easy to kind of lose track of your work. So I would like everyone to start off by numbering your equations. This is going to be how we show our work with these types of problems. So first thing I need to do is I need to look at my variables, and I need to pick a variable that I'm going to eliminate twice. So I think it'd be pretty easy to eliminate my x's twice. You have to do it in 2 different ways. So I could use equations 1 and 2, and then 2 and 3 and eliminate twice. It'd also be pretty easy for me to eliminate my y values twice. I mean, z wouldn't be that hard either. So we just have to pick one variable and eliminate it twice. Let's try to eliminate our y values twice. So here, I know that I can, if I use equation 1 in equation 3, here I have positive 2y, but here I would like negative 2y. So I'd like to multiply this equation by 2. So I'm going to keep equation 1 how it is. 4x plus 2y plus 3z equals 12. But again, since I want to eliminate my y's, I'm going to multiply equation 3 by 2. The way you can show that is like this, 2 times equation 3. This is showing that you're multiplying equation 3 by 2. So 6x times 2 is 12x. Negative y times 2 is negative 2y. 4z times 2 is 8z. And negative 3 times 2 is negative 6. And then I can see that if I add vertically, my y's disappear. I'm left with 16x plus 11z equals 6. So this is a new equation, and I'm going to give it its own number. This becomes equation 4, and you'll see that now it's an equation with only 2 variables. But remember, if we want to solve a 2-variable equation, we need 2 equations. So I have to eliminate y's again using a different set of equations. So equation 3 is a good one to use, and we haven't used equation 2 yet. So let's use equations 2 and 3. I can keep equation 2 exactly the same. And again, I'm trying to eliminate my y's again. You have to eliminate the same variable twice. So if I want to eliminate y's, that means I need to this to become positive 3, which means I need to multiply this equation by negative 3. So negative 3 times equation 3. So that gives me negative 18x plus 3y minus 12z equals positive 9. And then again, my y values, or my y terms, will cancel out, and I'm left with negative 16x minus 7z equals 2. Now again, I've created a new equation that I'm going to use, so I'm going to give it a number. I'm going to call it equation 5. Now if you look at equation 4 and 5, it's a system of two variables. We just have x and z, so we know we can solve this. Then on top of that, look at your x terms. We have positive 16x and negative 16x, so this is actually a really nice equation. They are already opposites, so all we have to do is line them up and add vertically. All right, so our x term disappears and we are left with 4z equals 8. So z equals 2. All right, so now we start back substituting. I need to substitute this into either equation 4 or 5 because they only have two variables. So to show that work, we're actually going to write out sub z equals 2 into, and then I'll sub it into equation 5. Negative 16x minus 7 times 2 equals 2. Negative 16x minus 14 equals 2. And then here we can see that x equals negative 1. And then now that we know two of our variables, we can substitute both of those into any of our original three, 1, 2, or 3. It doesn't matter. I'm going to sub both into equation 1. So sub z equals 2 and x equals negative 1 into equation 1. So we have 4 times negative 1 plus 2y plus 3 times 2 equals 12. And now we just have to finish solving. So negative 4 plus 2y plus 6 equals 12. We can combine like terms. Subtract 2, and we get y equals 5. So for this, instead of writing it as an ordered pair, we're going to write it as what's called an ordered triple. Always goes in alphabetical order, x, and then y, and then z. So negative 1, 5, 2 is our answer. So again, I would like to see every single person numbering their answers or their equations. If you're doing something like multiplying an equation, I want you to show that. When you have new equations, please give them a new number and please show all of your work. The reason why I'd like you to do this is because it's really easy to make a small mistake. And if you make a small mistake along the way, of course all of your answers are going to be wrong. But if I can interpret your work and find where you made that small mistake, I can give you a lot more points on a test or quiz. So it's super, super important that you show your work in this specific way. Okay, let's try another one together. So again, we're going to start by numbering our equations every time, and we're going to strategize to see which ones we want to eliminate. Maybe this time, let's try eliminating our x's. So if I want to use equations 1 and 2, that means I need to multiply equation 1 by negative 5 to make opposite coefficients. So negative 5 times equation 1, negative 5x minus 5y minus 5z equals negative 10. And then equation 2 can stay the same. 5x plus 5y plus 5z equals 3. So let's add vertically. So here you see, okay, my x terms cancel out, my y terms cancel out, and my z terms cancel out. So I'm actually just left with 0 on the left. But we have to see what the right side looks like. Here we have negative 10 plus 3, so it's negative 7. So here's one of those cases where our variables disappear and we're left with an equation that is not true. So remember, when we have this scenario, we say that there are no solutions to this system. All right, let's try one more together. So I am going to start by numbering my equations again. And then here, I see a pretty nice setup with the z's. Let's see if we can eliminate our z's twice. So we can start just by using equations 1 and 2. They are already opposites, which is really nice. X minus y minus z equals -3. So if I add vertically, I get 2x minus 2y. The z's disappear, equals -6. Remember, I am adding vertically, not subtracting. I'm adding. We have a new equation here, so I'm going to call it equation 4. Now let's see if we can do the same with equations 2 and 3, because we have opposite coefficients again. And remember, we need to eliminate the z's twice, the same variable twice. So x minus y minus z equals -3. 5x minus 5y plus z equals -15. Let's add vertically. 6x minus 6y, then here those cancel out, equals, and then we have -18. And I'm going to call that equation 5. So now we have two equations with two variables. One thing you might notice is that both of these equations can be reduced down. We could divide both sides by 2 here. We could divide both sides by 6. So if you notice that and you'd like to do that, you can. Or we can continue on. Let's say we don't notice that. So I look and I say, let's try to eliminate my x term. So I know I need to multiply this by -3. So we'll do -3 times equation 4. So that gives us -6x plus 6y equals +18. Equation 5 will stay the same. 6x minus 6y equals -18. Maybe you notice that the two equations are the same, they're just opposites. But either way, let's continue on. The x terms disappear, the y terms disappear, leaving us with 0. In fact, on the right, -18 plus 18 is also 0. So here are all of our variables have disappeared, but we're left with an equation that is true, which means that here we have infinite solutions. So now you've seen every possible type of answer. You saw a single solution, you saw no solution, and you saw infinite solutions. All right, I have this last problem for you to try on your own, so please pause the video and give it a shot. And make sure you're showing your work and numbering your equations. All right, go ahead and check your answers here. So the tricky thing about these problems is that there are so many different ways you can solve them. So I chose to eliminate my x values twice. Maybe you chose to eliminate your y values twice or your z values twice. So you should end up with the same answer, even if you use a different method, but your work might look very different than mine. So I did equation 1 plus -4 times equation 2, and then I did equation 2 plus 3. They were already opposites. And see how I numbered my new equations, 4 and 5. And then I did my equation 4 plus 17 times equation 5. And that allowed me to solve for z. And then I just started back substituting. And again, I'm showing exactly what I'm doing in every step. I'm actually writing what I'm doing, making it easy to follow, and also making it easy to catch a mistake if you make one along the way. All right, so that is all for today's video. Thank you so much for watching.